Let's start Chapter 19. It's about temperature. This is the first chapter for thermodynamics. Thermodynamics involves situations in which the temperature or state of a system changes due to energy transfers. Therefore, we need to define temperature. In daily life, we usually associate temperature with how hot or cold an object feels. It is unreliable, so we need a more technical definition of the temperature. To define temperature, we need to develop two more concepts: thermal contact and thermal equilibrium. If two objects are in thermal contact, then the energy can be exchanged between them. The energy is exchanged due to a temperature difference. Thermal equilibrium is a situation that two objects will not exchange energy either by heat or electromagnetic radiation if they were placed in thermal contact. The temperature can be defined by the zeroth law of thermodynamics. If object A and B are separately in thermal equilibrium with a third object C, then A and B are in thermal equilibrium with each other. Therefore, we can use temperature to determine whether an object is in thermal equilibrium with other objects. If two objects have different temperatures, they are not in thermal equilibrium with each other. Then they will exchange energy. We can use thermometers to measure the temperature. A common type of thermometer is a liquid in glass. The liquid is usually mercury or alcohol. To say an object is at a certain temperature, we need to define a temperature scale with some later systems that remain at constant temperature. A thermometer can then be calibrated using that temperature scale. A commonly used temperature scale is the Celsius scale. The ice pond of water is defined to be 0 degrees Celsius, and the steam pond of water is defined to be 100 degrees Celsius. Between these two ponds, we then divide it into 100 increments, called degrees. We can set up another set of temperature scale, called the absolute temperature scale. It is originated from the study on the constant volume gas thermometer. When we change the temperature, the pressure of the gas inside the thermometer will also change. We can plot a pressure-temperature graph using this thermometer. A typical PT graph of a constant volume gas thermometer is shown in the figure. We can use different gases to do the measurement. If we measure several times, as shown in this, we use free trial. For all free trial, the pressure escalates to 0 at a temperature of negative 273 degrees Celsius. We call this temperature the absolute zero. Absolute zero is used as the basis of the absolute temperature scale. The absolute temperature scale is now based on two new fixed points, the absolute zero and the triple point of water. The unit of the absolute scale are kelvins. The absolute scale is also called the Kelvin scale. The triple point temperature is 273.16 Kelvin. No degree symbol is used with kelvins. This figure shows some typical examples of phenomena on the absolute temperature scale. The temperature of absolute zero cannot be achieved. Now, let's move on to discuss about an equation which showed how the volume, pressure, and temperature of the gas of mass m are related. We call this the equation of state. We'll limit our discussion on ideal gas. For ideal gas, we assume the gas are at low pressures or low density. We can use the ideal gas model to make predictions about the behavior of real gas at low pressures. We usually will quantify the amount of the gas in a given volume using the number of moles n instead of the mass m. 1 mole of any substance is that amount of the substance that contains Avogadro's number of constituent particles. The Avogadro number is equal to Na, equal to 6.022 times 10 to the power 23. The number of moles can be determined by this equation, n equal to small m over capital M, and capital M is the molar mass of the substance, which can be found from the periodic table, right here. When we perform the ideal gas experiment, we can find the relationship between the volume, pressure, and temperature of the gas. For example, we can keep the gas at constant temperature and measure its pressure against its volume. It will give us the Boyle's law. We can do a similar measurement by keeping the gas at constant pressure or constant volume. It will give us two other gas laws. The equation of state for an ideal gas combines to give us this law, PV equal to nRT. This is also known as the ideal gas law. R is the universal gas constant, which is given right here. From the ideal gas law, you can determine that 1 mole of any ideal gas at atmospheric pressure and 0 degrees Celsius is 22.4 lit. Instead of the number of mole n, we can also express the ideal gas law in terms of the total number of molecules, shown here, where the capital N is the total number of the molecule, Kb is the Boltzmann's constant, which value is given right here. Let's look at an example. If we have a spray can where the initial pressure, volume, and temperature is given, if the temperature is increased, what is the pressure inside the can? Using the ideal gas law, PV over T equal to nR. In this question, the amount of the gas does not change, so we know that PV over T is the constant. And we further know that the volume of the gas does not change, so Pi over Ti is equal to Pf over Tf. And if we plug in the value given by the question, we can calculate the Pf is equal to 320 kilopascal. One point to note is that when we use the ideal gas law, the temperature is expressed in absolute temperature scale, that is in terms of the Kelvin. So we have to change the temperature from degrees Celsius to absolute temperature scale. That means the 22 degrees Celsius had to change to 295 Kelvin. And also for the 195 degrees Celsius, we have to change it in the absolute temperature scale, which equal to 468 Kelvin. Let's now move on to talk about Chapter 20, the first law of thermodynamics. Thermodynamics and mechanics were considered to be distinct branches of physics until the experiment by Joule and others showed a connection between them. The concept of energy was generalized to include internal energy, and the principle of conservation of energy emerged as a universal law of nature. We will first discuss a very important concept, the internal energy. Internal energy is all the energy of a system that is associated with its microscopic components. The internal energy includes kinetic energy due to the random translational motion, rotational motion, vibrational motion of the atom and the molecules. It also includes the potential energy between the molecules. However, the kinetic energy due to the motion through space is not included. That means if I hold a bottle of gas from left to right with some speed, the kinetic energy associated with this translational motion will not be included in the internal energy. Heat is defined as the transfer of energy across the boundary of a system due to a temperature difference between the system and its surroundings. That is, we use the term heat to represent the amount of energy transferred by this method. Joule performed an experiment to demonstrate mechanical equivalent of heat. The schematic diagram of the experiment is shown here. The falling rod rotates the pedals, which will cause the temperature of the water to increase. We can transfer the potential energy of the mass into the kinetic energy of the pedal and transfer it into the internal energy of the water, which is reflected from the increase in the temperature of the water. Joule found that it took about 4.18 joules of mechanical energy to raise the water by 1 degree Celsius. Sometimes we will express this 4.186 joules of energy as 1 calorie of energy. This is known as the mechanical equivalent of heat. If we provide an energy Q to increase the temperature of a substance by delta T, then Q equal to C delta T. Capital C here is called the heat capacity. It is defined as the amount of energy needed to raise the temperature of that sample by 1 degree Celsius. A more useful quantity, specific heat, denoted by small c, will be used. It is the heat capacity per unit mass. So C is defined as Q over m delta T. The specific heat is essentially a measure of how thermally insensitive a substance is to the addition of energy. The greater the substance's specific heat, the more energy that must be added to a given mass to cause a particular temperature change. The equation is often written in terms of Q, which reads as Q equal to mc delta T. There are some side conventions. If the temperature increased, Q and delta T are positive. It means the energy transfer into the system. If the temperature decreased, Q and delta T are negative. It means that the energy transferred out of the system. This table shows specific heat of some substances. You may notice that water at 15 degrees Celsius has a specific heat 4186 joules per kilogram degree Celsius, which is relatively high among other substances. It makes water a very good cooling agent. One technique for measuring specific heat involves heating a material, adding it to a sample of water, and recording the final temperature. This technique is known as calorimetry. Conservation of energy requires that the amount of energy that leaves the sample equals the amount of energy that entered the water, like this. The hot sample will give out energy, so its temperature will decrease. The cold water will gain some energy, so its temperature will increase. This energy exchange process will continue until the system comes to equilibrium. That is, the sample and the water has the same temperature, the final temperature Tf. Let's look at an example. A metal at 200 degrees Celsius dropped into a cup of water initially at 20 degrees Celsius. And if we know that the final equilibrium temperature is 22.4 degrees Celsius, we want to find the specific heat of the metal. This is the energy gained by the water. This is the energy lost by the metal. Tf is 22.4 degrees Celsius, Tw is 20, and Ts is 200 degrees Celsius. The specific heat of the metal is equal to 453 joules per kilogram degree Celsius. If we provide energy to water, the temperature of the water will increase. When the temperature of the water reaches 100 degrees Celsius, the boiling point of the water will change to steam. We call it the phase change. A phase change is when a substance changes from one form to another. Two common phase changes are solid to liquid, we call it melting, liquid to gas, we call it boiling. It is important to note that during a phase change, there is no change in temperature of the substance. For example, in boiling, the increase in internal energy is represented by the breaking of the bonds between molecules, giving the molecules of the gas a higher intermolecular potential energy. We will call the material existing at a higher temperature the higher phase material. If the initial amount of the higher phase material in a system is Mi, then the amount of energy Q required to change the phase of an sample is given by L equal to Q over delta M. Delta M is the change in mass of the higher phase material, which equal to Mf minus Mi. L is called the latent heat of the material. We'll usually express the equation as Q equal to L delta M. There are two types of latent heat. The latent heat of fusion is used when the phase change is from solid to liquid. The latent heat of vaporization is used when the phase change is from liquid to gas. This table shows you some typical values for the latent heat of fusion and vaporization for different substances. This graph shows you the energy required to change an ice at a temperature of negative 30 degrees Celsius to a steam of a temperature 120 degrees Celsius. You may observe that most of the energy goes to the latent heat of vaporization, that is, to change the water to steam. In this example, we want to calculate the mass of steam initially at 130 degrees Celsius to warm 200 grams of water in a 100 gram glass container from 20 degrees Celsius to 50 degrees Celsius. The steam will undergo three processes. First, you have to decrease the temperature from 130 to 100 degrees Celsius. Then you will condense to water. That means change from gas to liquid. Finally, you will decrease its temperature from 100 degrees Celsius to 50 degrees Celsius. The energy released are given by Q1, Q2, and Q3, respectively. We add Q1, Q2, and Q3 together to get the total amount of the energy released by the steam. The energy required to raise the temperature of the water and the glass from 20 degrees Celsius to 50 degrees Celsius is given by this equation. The energy gained by the water and glass is equal to the energy released by the steam. The mass of the steam required is just 10.9 grams. Are you surprised by this very small amount of steam required? In the following, we will derive the first law of thermodynamics. To do so, we have to define several physical quantities first. The first one is work. Work can be done on a deformable system, such as a gas. Consider a cylinder with a movable piston. Since the gas will exert pressure on the piston with some area. Pressure times the area gives you a force. If the piston moves with some displacement, work is done. If the piston is pushed downward by a force through a displacement of dy, then the work done on the gas is given by this equation. dW is equal to negative P dV. And dV is the change in the volume of the gas. From the equation dW equal to negative P dV, it means that if the gas is compressed, that means dV is negative, then the work done on the gas is positive. If the gas expands, dV is positive, then the work done on the gas is negative. If there is no volume change, then the work done is zero. The total work done is given by this integral. The state of the gas at each step can be plotted on a graph called a period diagram if the pressure and the volume are known at each step of the process. The curve here is called the path. The work done on a gas equal to the negative of the area under this PV curve. The area is negative here because the volume is decreasing, resulting in positive work. Please note that the work done depends on the path taken. Consider these three processes. Each of these processes has the same initial and final state. And the three processes have taken different paths. The work done is different in each process. The work done depends on the paths, although they have the same initial and final states. The first law of thermodynamics is a special case of the law of conservation of energy. It states that delta E internal equal to Q plus W. Delta E internal is the change in the internal energy. Q is the energy transfer of the system with the surrounding. W is the work done on the system. It is a special case when only the internal energy changes and the only energy transfers are by heat and work. If we consider an isolated system, which it does not interact with its surroundings, so no energy transfer by heat takes place, and the work done on the system is zero. So Q and W equals 0, and delta E internal equals 0. It means that the internal energy of an isolated system remains constant. We usually will focus on cyclic processes. A cyclic process is one that starts and ends in the same state, like this. A cyclic process will not be isolated. On a periodic diagram, a cyclic process appears as a closed curve, like this. Since the internal energy is the state variable, it must be 0 if the system starts and ends in the same state. A state variable means that if the system is at the same state, that means if the gas has the same pressure, volume, and temperature, then it will have the same internal energy. Therefore, in a cyclic process, the change in the internal energy is 0. Then according to the first law of thermodynamics, Q equal to negative W. In a cyclic process, the net work done on the system per cycle equals the area enclosed by the path representing the process on a period diagram. We look at 4 applications of the first law of thermodynamics: adiabatic, isobaric, isovolumetric, isothermal. We'll look at them one by one. Adiabatic process means that no heat exchange, that is Q equal to 0. From the first law of thermodynamics, when Q equal to 0, delta E internal equal to W. That means the work done on the gas is used to change the internal energy of the gas. If the gas is compressed adiabatically, W is positive, so delta E internal is positive, and the temperature of the gas increases. That means if you compress the gas very fast, you can increase the temperature of the gas. In opposite, if you expand the gas very fast, you can decrease the temperature of the gas. A very special example called adiabatic free expansion is shown here. If it is just that the membrane is broken, the gas can expand freely. No work is done, and no internal energy change. So there will be no change in the temperature. Then we look at the isobaric process. Iso means equal. Baric is related to pressure, so isobaric means constant pressure. If the pressure is constant, then the work done can be calculated using this equation. The values of the heat and the work, and also the change in the internal energy, are generally both non-zero. This process can be easily achieved by just moving the piston under atmospheric pressure. The isovolumetric process is the constant volume process. Since the volume does not change, the work done is 0. From the first law, the change in the internal energy equal to the energy transfer. It means that if the energy added by heat to a system which is at constant volume, then all the energy transfer will remain in the system as an increase in the internal energy. It is just like if you use a fire to heat up a bottle of gas, then the temperature of the gas will increase because the volume cannot change. All the energy transferred from the fire will go to increase the temperature of the gas. Isothermal process is a constant temperature process. If there is no change in the temperature, then the internal energy will not change. So we have Q equal to negative W. It means that any energy that enters the system by heat must leave the system by work. This period diagram shows an isothermal expansion. The equation of the curve is PV equal to nRT. Because T is a constant, so PV is a constant. This curve is called an isotherm. To calculate the work for isothermal expansion, we use this integral. Applying the ideal gas law, PV equal to nRT, we can express P in terms of nRT over V. Because T is a constant, we can take it out of the integral. Evaluating the integral, it will give us W equal to nRT non Vi over Vf. If the gas expands, that means Vf larger than Vi, then W is negative. If the gas compressed, that is Vi larger than Vf, W is positive. Consider an example of isothermal expansion. If 1 mole of an ideal gas at 0 degrees Celsius expands from 3 lit to 10 lit, the work done can be calculated using this equation, which is negative. In part B, we want to calculate the energy transferred by heat occurred between the gas and its surrounding in this process. We apply the first law of thermodynamics. Because it is isothermal, so the change in the internal energy is 0. Q equal to negative W, which is a positive value. It means that we have to provide energy to do this isothermal expansion. Part C. If the gas is returned to the original volume in the isobaric process, how much work is done on the gas? For an isobaric process, the work done can be calculated using this equation. Using the ideal gas law, P is equal to nRT over V. The work done is 1.6 times 10 to the power 3 joule. Consider an example of boiling water. The water is boiled under atmospheric pressure, so it is an isobaric process. We want to find the work done in the expansion and the change in internal energy of the system. For an isobaric process, the work done can be calculated using this equation. If we load the energy transferred by heat, we can calculate for the change in the internal energy according to the first law of thermodynamics. We can use Q equal to L delta W to calculate the energy transfer for the water to change to steam. Then the change in the internal energy is equal to Q plus W. There are 3 main mechanisms of energy transfer in thermal processes. They are conduction, convection, and radiation. Conduction, in atomic scale, it is an exchange of kinetic energy between microscopic particles by collision. Therefore, it needs physical contact for the 2 objects if conduction has to take place. In general, metals are good thermal conductors, and paper gases are poor conductors. Convection is the energy transferred by the movement of a substance. It happens in fluid, that is, liquid and gas only. All objects will radiate energy continuously in the form of electromagnetic waves if they have non-zero temperature. Radiation does not require physical contact. A DeWalt flask is a container designed to minimize the energy loss by conduction, convection, and radiation.